Assalamualaikum and very good morning. How are you guys? Let us continue this topic on material balance on a multiple unit process. And before that, I wish you Selamat Hari Raya and welcome back. Okay, let us continue. Let us talk about recycle. What does it mean by recycle? When you have a chemical reaction, for example, A into B in a reactor, okay, with 100 kg of A and we expect to have 100 kg of B, that is 100% conversion. However, in a reality, okay, we might not get that 100% conversion. With that, we only get about, let's say, 70 kg of B produced, meaning to say the conversion is only 70%. In this case, in reality, it's occur and it cannot be avoided because some of the reaction, the highest conversion is that we cannot do anything. We cannot change the conversion from 70% to 100%. However, we can recycle back the unreacted reactant into the, meaning to say, we can recycle back this 30 kg of A goes back into the reactor. Okay, and we're going to take a look on how to do a material balance for this recycle stream. Okay, and you might be asking me why we need to recycle. The first one, because we want to have the highest conversion as possible, because it's about money. Okay, when we have a reactant turn into a product, if we have 100% conversion, that is the best and ideal condition, and it will give us more money profit, because a product 100% reactant being converted to 100% product. But in reality, it never been the case. So in order for us to increase our yield, to increase our product, we do a recycle. Okay, we don't want to waste this unreacted reactant. Okay, so we do a recycle. In industry, practically we do a recycle to save money. Okay, the more product, more money. Less product, you will lose some money. Okay, so in order for us to do a recycle, we need to separate between the product and the unreacted reactant. We cannot just simply directly recycle it. We have to take the product. Okay, in order to do that, you will need another equipment. Okay, you will need another equipment named separator. What is separator? It is an equipment to do a separation. So here we have separator to separate. Okay, this separation you will learn in detail in your third year in a separation course. Okay, specifically, and you will know what is the equipment, what are the equipment being used to do a separation. Okay, so this separator is a just a general name of this separation equipment. Okay, and we have to separate between the product and the unreacted reactant, not the we can say a reactant, it is unreacted. Okay, and we do a recycle. This blue line is a recycle stream. Okay, so to do a material balance about it, later on we will go into a detailed example. This is how people do a mass balance about it. Okay, and you have let's say you have 110 kg of A goes into a reactor, and here you have additional from a recycle stream and this A become 200 kg before it goes into B. And as you can see here, there are also B, which is a product, been included. Okay, because this separation also is not 100%. It doesn't separate A to B 100%. Okay, and also some of a risk, quite a small amount of A still remain in the product. And later on, you will do another separation unit to really separate A and B. It could be a multiple separator. Okay, don't worry about that. But here we're going to see how to do a material balance about it. Okay. For example, I put it a recycle with a reaction. And this recycle stream could be from a non-reaction whereby you separate from, not from a reactor. Okay. If there are a reaction, it should be involved an equipment named reactor. But without a reaction, you don't need a reactor. Okay, for example, when you do, in order for you to do a material balance, consider this as your boundary condition, your reactor as your boundary condition. Okay, your separator also. To do a material balance for this recycle stream together with a multiple unit, okay, when we have more than 2 units, we call it a multiple unit with a recycle stream. Remember that you have to do a boundary condition. You have to set a boundary condition. So it could be at your reactor, it could be at your separator, and it also may be your overall boundary condition, meaning the outer layer of your block diagram. Okay? And don't forget another boundary condition at a mixing point. A mixing point from a recycle stream. The next thing to do, I believe you know, you have to apply a degree of freedom at each of these vectors. Okay, let us jump to the example. Okay, before that, I would like to introduce to you the formula to calculate conversion. There are two types of conversion. The first one is an overall conversion, whereby this overall conversion apply when you have the outer boundary condition, whereby the value of reactant goes into the process minus the value of reactant out from the process divided by how much the reactant input to the process. This is known as a boundary. This is known as an overall conversion. And another type of conversion is when you have at that particular reactor. At this reactor, at this boundary condition, it is called single pass conversion. Okay? I really hope that you can differentiate between overall conversion and single pass conversion. Okay? Overall conversion is applied for the overall boundary condition. Okay, how much the reactant goes minus how much the reactant left in the product. How much the reactant been the output. And we have also a single pass conversion whereby we calculate at the reactor itself. Okay. For example, here, okay, to calculate an overall conversion here, okay, which is at this outer boundary condition, we take a look on, we take 75% of A, 75 mole of A minus 0% of A here. A is 0%. divided by how much the A goes in, same 75%, and we have 100% conversion. Okay, and how about single pass conversion? Single pass conversion meaning to say when you have a boundary condition at your reactor, and the way to calculate it, which is 100 kg, we took it here 100 because this 100 kg goes into the reactor minus how much the A been unreacted over 100 kgs go in, we have only 75 conversion. Okay, so we have 100 kg 100% overall conversion, and for the single pass conversion we have only 75%. Okay, I really hope that you can differentiate between single pass conversion and overall conversion. And why we need recycle? Because we want the overall conversion become 100%. So we keep on recycle back the unreacted reactant so that the reaction can be further and we don't waste any reactant. Okay, let us take a look another example on how the recycle been done with a reaction. Okay, so we have here dehydrogenation of propane. Okay, and as you know, CH3 H8 is a propane become a propylene C2H6, and it remove another hydrogen from that bonding. Okay, last time you learn in your chemistry during your matriculation, you learn about dehydrogenation process, whereby from a single bond become a double bond. Okay, and here in a chemical engineering, the same process, the same reaction, however it came with a material balance and it came with an equipment used to do the reaction. Okay, last time you just learned about the C bond and CH, right? Remember that? Remember that C and become C like this, right? You learn during your matriculation, but here we learn about how to do the material balance together with what are the equipment involved in industrial, meaning to say in a large scale. Okay, so here we have this reaction with 90%, 95% of overall conversion. Okay, overall conversion, meaning to say the outer boundary condition, it has 95%, and the product are separated. Okay, is separated into two streams. The first ones contain hydrogen, propane, and 0.55% of propane that leave the reactor is taken off as a product, and the second stream, which contain the balance of unreacted propane and 5% of propylene in the first stream, is recycled back to the reactor. Okay, and then you have to calculate the composition of the product and the ratio, more recycled to more fresh feed, and with a single pass conversion. That is the thing that you have to calculate. So based on this statement, based on all this sentence, you have to draw your block diagram. The first one, you will need a, let's see the example. The first one is a reactor. For the reaction to took place, okay, for the reaction took place in a reactor, and you will need, okay, of course, don't forget your arrow. You have a reactant and a product, and remember the words, the product being separated, meaning to say you need another equipment named separator. Okay, and this separator will separate into two streams. Your product being separated by using a reactor into two streams, and another stream being recycled back to the reactor. Okay, what are the information we have? Okay, we have to extract all the information from the sentence, and we have to define our unknown. Okay, there's no information about how much the propylene and propane goes into a reactor, and there also there's no information about how much all these three chemical came from the reactor, but we have information about what is the product. Okay, the first one is we have the about 0.55% of N3 based on the sentence. Okay, you can check back this. Okay, based on the sentence. Okay, and then it also mentioned that how much the propylene been recycled back, the propane, but we don't know exactly the value of mole, how much the mole of each of these stream. So we put it N1 and 2, okay, because N is for the mole. So we assume, okay, we take a basis of fresh feed. Okay, we take a basis of 100 mole to be our fresh feed. Okay, and the first one you need to do is, after you labeling all the unknown, you have to do a boundary condition. Okay, when you have this boundary condition, okay, and what next? With this boundary condition, you have to do a degree of freedom. Okay, to do a degree of freedom, okay, you have three unknown, okay, which is N6, N7, and N8. There are three unknown. Because of this is a reaction, you can do atomic balance. Okay, you can do atomic balance, which is for C and H. Okay, and you have one relation, which is 90% of a overall conversion. Okay, you have 95% overall conversion. Okay, so it will give you 0 degree of freedom. Okay, how about when you have a boundary condition at a mixing point? Okay, here at a mixing point here. Okay, same, you have to do a degree of freedom. You have 4 unknown, which is N1 and 2, together with N9 and N10. Okay, N1, N2, and N10. So, but you can only do 2 molecular balance, okay, for propane and propylene, and you will have another 2 degree of freedom. How about at a reactor? Okay, at a reactor, when you have about 5 unknown, N1 to N5, you don't know, and you can only do 2 atomic balance, and you will have another 3 degree of freedom. How about at separator? Same as previously. Okay, so you have 8 unknown. Okay, you can count, and 3 and 4. I believe I left some space for you to write it. Okay, you can write it by yourself. Okay, and the 3 unknown from overall balance, which is N6, N7, and N8, you can determine from here, because here is 0 degree of freedom. Okay, so you can determine this. When you can determine this, so it will reduce the unknown from here. Okay, and then you can do 3 molecular balance. Together with, you have 2 relation, which is this one and this one. Okay, so you have another 0 degree of freedom. Okay, so to start with, you have to start with 0 degree of freedom first. So let us start with the overall conversion first. Okay, when you have overall conversion and you have the information about 90% of overall propane conversion, meaning to say another 5% is unreacted. So straight away you can find the value of N6. Okay, so your N6 is about 0.5, then time 100 you get 5 mole. Okay, so your N6 is 5 mole because of 95 conversion. 95 conversion meaning to say 95% of propane being converted into propylene, or there are left 5% of unconverted propane. That's why you can directly calculate your N6. Okay, if you still don't get it, you can leave a comment below. Okay, the next thing to do is you can do the C balance. Input is equal to output. Although this is a reaction, this process involves reaction, but the overall balance or the atomic balance, okay, atomic balance can be written as input equal to output, although at a reaction, because there is no generation or consumption of the specific atomic specific atom. For example, the carbon. Okay, there is no generation of new carbon. There is no generation of new hydrogen. Just the molecular, just the arrangement of the C and H make it as a different molecule, but not the atomic. Okay. So for the C balance, okay, you have input equal to output. You have 100 mole of propylene, for propane, and it has three atom of carbon, and for the output you have N6. You have N6 with 3 atomic balance, and you have N7 with also 3 atomic balance. So we write here, and this value we already get, so we can get the value of N7. Hey, remember, for 0 degree of freedom, you can straight away get your unknown value. Okay, same goes when you have the balance for H. Okay, input equal to output, whereby you have 8, right? You have 8 times 1 mole, 100 mole. Same goes with your output. You have N6 times 8. Okay, you have N7 times 6. And you have another N8 times 2. Okay, because you already know what is the value of N6 and N7 previously, you can get the value of N8. Okay, therefore, you can calculate the composition of the product, okay, with N6, okay, N6, N7, and N8. You can calculate the composition and you get this number, okay, 5 over 5 plus 95 plus 95. You should get this. Okay, same goes when you have 95 over 5 plus 95 plus another 95. You should get this value. Same goes with this one. Okay, and if you still have problem about this, you have to refer back your chapter, maybe your previous lecture on how to calculate a composition. Okay, so we already solved for 3 unknown at a overall boundary condition. Next, we move to another equipment that also have 0 degree of freedom, which is at the separator. Okay, and remember this, you already know the value. Okay, when you already know this value, you can continue to calculate the unknown. Okay, so for the N6 is equal to 0.00555 N3, so you can straight away get the value of N3. Okay, and then for the value of N10 basically is 0.5% of N7. Okay, all this information is stated in the equation. You have to go back there. You have to reread it so many times so that you can relate. Okay, but still, if you have a problem to understand it, you can refer me back. Okay. So, at separation unit, when we do a balance, again, we do a balance because at separator there is no reaction, so we just directly use input equal to output. There is no generation, there is no consumption because here at a separator, no reaction. Okay, so we do a balance for propane. We have N3 propane plus N6 propane. N3 is input equal to output N6 plus N9. Okay, we already know what is N3. Okay, and we also already know what is N6. So we can determine what is N9. Okay, try by yourself. Did you get this number or not? And I believe I leave there some space for you to write. You have to try by yourself. If you just listening, it's not going to help you to understand. Okay, you have to try by yourself. Okay, and then at a mixing point, okay, once you settle at N at a separator, okay, you get the value of N3 and 9, okay, but you still cannot get the value of N4 and N5. Therefore, you move to a mixing point. Again, we do a propane balance there, okay, whereby you can calculate the value of N1. Okay, you can calculate the value of N1 because you already know what is your N9. Okay, you get the value of N1. Okay, once you get this, you can determine your recycle ratio, meaning to say the total amount of recycle, the mole of recycle over the mole of fresh feed. Okay, so you have N9 and N10. Okay, and you have 100 mole of fresh feed, so you get this number. Okay, your N9 is, what is your N9? Your N9 is this one, and your N10 is this one. You get approximately about this. Okay, so how about at your reactor? You need to calculate. You still have an unknown, which is your N2, N4, and N5. So what you need to do, okay, at a boundary condition of a reactor, you can calculate your single pass conversion. Okay, remember the formula for single pass conversion. How much the reactant goes into the reactant minus how much it's left the reactor divided by how much it's the input. Okay, that's it. Okay, meaning to say you don't need to calculate the value of N4. You still can determine the value of it. You already answered all the question, the recycle ratio, the single pass, and the composition of your product without knowing what is the value of N4 and N5.